Section 21.6, the torque on a current-carrying coil. So if you have a loop that has current and it's between two magnets, there's two forces that act on either side of the loop. And it turns out they have equal magnitude, but you could apply the right-hand rule and show that they're opposite in direction in terms of the forces. And this is actually good because it means it can create a rotation. So if we look at side one that has a current coming out at us, right? So this is looking at like a top-down view and the wires coming at us. And we could again use our right-hand rule, current coming at us, magnetic field pointing to the right. The force on that one is up. On side two, the current is going away from us, going into the screen, down on the side one, but into the screen. Magnetic field is still pointing to the right, which means our force is down in the negative direction. Anytime you have forces acting at a distance from the shaft, you're going to get a torque, right? It's going to produce this rotation. So that's what we're studying here. Taking a closer look, the loop tends to rotate such that its normal, the perpendicular, what pierces the loop, becomes aligned with the magnetic field. So if initially the magnetic field is just hitting the wires, that's going to create a rotation until it's able to pierce the loop, right? That's where you have maximum torque when the normal is perpendicular to the magnetic field, and then zero torque once the normal is lined up with the magnetic field. At this point, the forces are opposing, and it's not actually going to rotate or cause a rotation if it's not rotating. And we can calculate how much torque there is depending on this orientation. So if we went to set up the net torque, remember our symbol for torque is the Greek letter tau. It's a curvy T. And it'll come from the current times the length of the wire times the magnetic field. And there's two different components here. One is from side one side, the other's from side two side. So we have half the width that's going into this area times the sine of the angle between them, but they're at the same angle. So these end up being the same terms. And if we add the half width plus half width, it just becomes a full width. And so then notice we have a length times a width, which is just going to give us an area. And so instead of a length, we now have an area in the equation in order to calculate torque. The other thing to consider is this is just for one turn, but if we had more turns, just as we saw in the last example, we would need to multiply by n. And that's what's done here. We've added in a number of turns in the wire, multiplied by the current, by the area, times the magnetic field, times sine of the angle that the normal makes relative to the magnetic field. Another important note here is this is how we calculate the total torque with all of these terms. But another important factor that pops up in solving these problems is something known as the magnetic moment. And the magnetic moment is everything in front, the number of turns times the current times the area. So now that we've seen these equations, let's take a look at an example. Example 6, the torque exerted on a current-carrying coil. A coil of wire has an area of 2 times 10 to the minus 4 square meters, consists of 100 loops or turns, and contains a current of 0.045 amps. The coil is placed in a uniform magnetic field of magnitude 0.15 Tesla. A, determine the magnetic moment of the coil. B, find the maximum torque that the magnetic field can exert on the coil. So we remember that magnetic moment we just saw is N times the current times the area. And we have all those things, right? The area is given to us directly. We know the number of turns is 100, and we know the current in amps here. For the maximum torque, we'll just need to take this magnetic moment and multiply by the magnetic field, multiply by B. But what about that angle? This problem doesn't specify an angle directly, and we need that if we want to then calculate the torque. So the key here is in the question of the problem. Notice it asks for the maximum torque. The maximum torque has a very specific angle value, and that is an angle of 90 degrees. That is the very largest that sine can be. You get the maximum torque when the normal is perpendicular to the magnetic field. Now that we have that, we are in good shape to go. Let's take a look. So magnetic moment, NIA, we multiply those out, and the units of it are just what we have here, amps times square meters. Fairly straightforward. The torque is just taking that result, the magnetic moment, and multiplying by the magnetic field times sine of the 90 degrees. And it comes out to our units of torque, if you remember them, are newtons times meters. I know it doesn't look like that when you have amps times square meters times Tesla. But if you look at how amps break down and how Tesla break down, you'll find that the coulombs cancel out and you're left with the units that add up to newtons, which are kilograms meters per second squared with an extra meters there multiplied in. So this gives us an example of the torque exerted on a current carrying coil, and you might be wondering, why do we care? Well, one important application of this is the concept behind a DC motor. DC motor is when you have a source of direct current, like a battery, and it makes something spin. So a basic little motor is often a DC motor. A CD player, right? That's often powered with a DC motor if you have a Walkman, or in your computer if you still have a DVD drive, or so many other things. Basically, anytime you have something cordless that has motion, the fan in your computer is powered on a DC motor. So how does this work? Well, whatever you want to turn, to move, is connected to the shaft, and then we have the wire that's going to have current passing through it, and the magnet, north-south. But we remember, it's going to experience a torque up to the max, and then there's not going to be torque. And then if it keeps going, it's going to be the wrong direction. So that's where these half rings are really important, and they help us out. Let's take a closer look on the next slide. So if we have current from our battery source, right? The current's passing through, and it goes through the left side here and down on the other side and back to the battery. And so we could show, using the right-hand rule, that the force is up on the one and down on the other side, and that produces this rotation. In the middle, there's no more force acting on it, but it's okay because it's already moving. So it will keep moving and swing on, and this is when it's not in contact with either of the wires. There's no current flowing. Notice though, when it reconnects, it will now have switched the orientation. So even though we started out on this side, that side continues on and is now over here, and it will now be connected to the negative side instead of the positive side as this spins around a little further. So it switches so that now the current, once it reconnects, will be coming up through the opposite side. And that will then boost it. It will give it torque to continue rotating in that same direction. So this is a really clever, simple setup that doesn't take up a lot of space and can get things spinning. And there we have the torque on a current carrying coil.